So in deriving these results, we use the fact that the Schrödinger equation is linear and therefore the resulting evolution is linear. Now the resulting evolution being linear means that you can describe it using a linear operator. In other words, if you know what happens to each basis state as it evolves in time, then you can work out what happens to a general state. And you can encode all of that in the evolution operator. We can work out what this time evolution operator is because it comes from the Schrödinger equation up here. So I know that the time derivative of this thing is, and so I can work out what the time derivative of that thing is. Straight from the Schrödinger equation. Over here, you'll note that the state itself, this is the state at some initial time t0, that doesn't depend on t. So this state isn't changing as we change t. The only thing that's changing is our evolution operator. So our evolution operator is the only thing that we need to take the derivative of, and so this thing can come straight out. Remember that when we have operators, we can't change the order of things, so it still needs to be on the right. So this equation is true, but this equation is true for all possible states. And if this is true for all possible states, then the bit in the brackets here must be true in general. So we have, which means that we can work out how this evolution operator evolves over time. We also know its initial state very simply. If this is t0, t0, then what we're doing is we're trying to evolve the state at t0 to the state at t0. So this has to be the identity. So when t equals t0, this is just the identity, and then as we change t, it follows this differential equation, and so we can work out for all time. Now again, this kind of equation is exactly the kind of equation we know the solution to. It's the exponential. This is for a constant Hamiltonian. So two things here. The first is it's very easy to show that this is the correct answer, because if we put t equals t0, then we indeed get the identity. The exponential of 0 is the identity. And secondly, it's very easy to plug that into this equation here and show that it solves the equation, and therefore it's the right solution. We may be a little bit concerned about what the idea is when having an exponential of an operator. We know what the exponential of a number is, but we don't necessarily immediately understand what the exponential of an operator is. Now in general, functions of operators work exactly the same way as functions of variables. So if I take a function, just a general function f of x, and I expand it in a Taylor series, then if I take that function of some operator, it's exactly that Taylor series of the operators. So we can always expand this exponential. We know the exponential is just this Taylor expansion, and so we can use that to show that this holds. Now this time evolution operator has a very important property. If you take the Hermitian conjugate of it, you find that it's its own inverse. And that's called a unitary operator. So try showing that the time evolution operator is a unitary operator.